Hi, we are Yulai, Han and Jiakang from Team 66. We have used three techniques, which are BRFS, Q-Learning, and MCTS, and developed the corresponding agents. Through experiments, we found that Q-Learning does not perform well, and the agent created by combining BRFS and MCTS has the best performance, which is our final agent. BRFS is our baseline model agent. By checking all possible moves, BRFS will choose a move with the highest score. We need to care about corners and edges, which may influence the win rate and the state of the game. If the action runs within the time limit that we set, we could always get a solution that gains the highest score for the current move. However, if the action runs over the time limit, we make a random move, which is probably not the optimal solution. Besides, BRFS is relatively easy to program, but is not effective and efficient enough compared to other algorithms. From the GNF, we could see that the move could always be optimal for the current situation as long as it's within the time limit, but we could also see that sometimes the move seems not useful. This is because action is over the time limit and has to make a random move.
In the Q-learning algorithm, as the number of iterations increase, the agent becomes more stable to the environment. However, the initial futures weight and the format parameter setting is unreasonable, which may lead to a low winning rate. In the diamond of this experiment, it can be seen that if the last two moves are 1, the agent score is 34, and it will win. If it moves to 2, the agent score is 27, and it will fail. Therefore, the winning rate will be greatly reduced, from which we can analyze our calculated format at that time. Since one future weight C5 represents number of self-color on permanent edges, after the weighted is updated, the weight of C5 is a navigation value. That is, in the same saturation, the more steps you take, the smaller the final calculated Q value. That is to say, the direction of this weight value of C5 is wrong. This may be a problem with the initial weight or the weight update function.
So our third algorithm is mental color tree search. Mental color tree search runs a large number of simulations in each round. After the simulations, an action that has the best overall result will be chosen. The first challenge we face when using a mental color tree search is the reward function design. The reward function should be designed well to achieve a good performance. So we set the difference between the player score and opponent score at the terminal state as the reward. Besides, there should be a trade-off between the time limit and the performance of the algorithm, which means we need to use relatively simple strategies while ensuring the high performance of the algorithm. So we used UCT algorithm in the selection phase, and for simulation, we used the corner policy instead of random selection to achieve a better result. The advantage of mental color tree search is it has a relatively high performance without knowing much domain knowledge. What the drawback is, the performance of mental color tree search is highly dependent on the number of simulations, which means our agent cannot perform well enough at the beginning of the game. So our final agent is a combination between mental color tree search and breadth search. Realizing MCTS bad performance at the beginning of the game, we use breadth search in the first 10 rounds of the game and use MCTS in the rest of the game. The live demo on the right shows the corner policy of our agent. We can see our white-colored agent will always try to occupy the corners and avoid occupying the positions that are adjacent to the corners. We can see the 4 corners are all occupied by our agent and we achieve a good result in the end. For future improvements, we believe that adding domain knowledge to UCT calculation can achieve a better result. Also, heuristics or more complicated strategies can be added to the simulation phase if the time limit is longer than 1 second.